Good morning,
Hey, good morning.
calculus team. Raymond, how was your weekend?
I work on the weekends, so just working and
Yeah,
playing guitar when I have free time.
nice. Where do you work?
Fred Meyer.
Oh, sweet.
And
South
Grant.
one or the north one?
And
GP.
Grant. Yeah.
Oh, that makes sense because you were in the Grants Pass calculus sequence. Got it. Let's see. I think I opened up. I better look really quick. Let's just take stock of where
Your
we are.
weekend.
Okay. My weekend was generally good. Had a, I guess we'll call it a celebration of life for a kayaker friend that died on the river a week ago, which was kind of a bummer for his family and all that. So that was kind of hard. And
Dang.
hosted that out at Cantor Buckley, and I did the emceeing for that and wrote a poem, went outside of my math brain and wrote a poem
Nice.
and read it and gave it to the daughter. So that was good. But yeah, a little bit of a strange weekend. So, but overall good. It's a gift to be alive. That's the thing that you got to keep straight. Every day is a gift and got to enjoy it as such. Well, let's see. Yeah, taking stock of where we are, you may notice there is one more assignment. I grouped 13.3, I'm sorry, 14.3 and 14.4 together. There's only, oh, actually, I think the date's wrong on it, which means it's probably not open at all. I'll fix that. But there's only a few questions in here, which is kind of awesome for you. Let me make sure I'm looking at this: length of the curve, speed of the curve. We're basically going to just look at a couple of applications of all of this vector business, vector valued functions. And
Are we not going to do 14.5?
we'll see. Kind of depends on what we get through. It's a little hard for me to tell because our book that we're following, the Pearson book, is kind of not the same as my open math. And the problems here, weird enough, difficult enough. There aren't a ton of choices out there. So that's part of what feeds into this. So we'll just kind of see how far we get today. One way or another, even if you sort of get a little bit extra time to study, we'll take the last test most likely on Thursday. But we'll see. We'll talk about that. Should know after today. So I do want to start off with something kind of cool. I sort of labeled this question the Falcon problem. One of the things I hope that you notice, and I want you to kind of stare at this with me and see if you can gather this yourself, but is this big enough for you to see the equation over here? Notice again, we call it a vector valued function, but it's really just a parametrically defined equation with its x, y, and z components, functions of t, the parameter t. And so we have 3 cosine of 2t. So you should think, oh, cosine wave, I know what those look like. And then t squared, oh, parabola. And then 3t, oh, that's just a line. And so, if you look at it kind of eliminating one of the directions, notice we're looking straight down from the top right now since we got red and green. And so we're seeing, I guess you could say, a modified cosine wave because we have x and y available to us. We don't see z, we don't see it coming toward us. So then if I rotate it in this direction, what do you see there? And are you surprised to see that? I want you to think about that for a second. Have you memorized the colors, green and blue, or y and z? So if you look at y and z, are you surprised by what you see there? So since I see a t and a t squared, I'm not surprised to see a parabola. So then I think, oh, it's a parabola. but it's sort of missing the cosine, right? It's missing the cosine of it. And so if I was to look down from the top, I would see the cosine aspect of it. Oh, okay, that's kind of cool. Let's see, what if I look at it from this direction, eliminating y? Notice I didn't get that perfect, but if I eliminate y, now you have a z and an x. And so this is the purest form of the cosine wave. And so it's really kind of funny how like you stare at these things and it just looks like some wonky, piece of wire that got bent into some weird direction. But yet if you eliminate one of the dimensions of it, you can sort of see, you can kind of, you can tell that you could actually get good at predicting what these graphs look like if you had some reason to do so. So that's kind of cool. And then I'd like you to stare at the other things I did over here. Can you pick out what's going on over here? So we got f equals 3 cosine of 2a, a squared 3a. What the heck is that doing? And then you got v equals v, what's that? And then you got b equals, and you got u equals, and I've got this slider over here so you can, this is
V is the magnitude of something.
Yeah, I like how you're recognizing the Pythagorean theorem in V.
Is it it looks like it might be the magnitude of the velocity,
Why do you say velocity? You're correct.
because -6 sine of 2a is the derivative of 3 cosine 2a.
Awesome, exactly right. Notice if you take derivatives, the derivative of cosine is sine, the derivative of t squared is 2t, but then remember you're going to square it as a part of the Pythagorean theorem, like Raymond pointed out. And so yeah, that's actually the velocity. And so this is a good problem. I called it the Falcon problem, just only, or the Falcon graph, just because you can at least imagine a bird taking off and just flying along in some kind of a weird path. So one thing I want to show you, just so that you walk away, we're on our last week here with just kind of a cool conceptual understanding, is notice the derivative of that. And you can see over here that the green vector is based off of the derivative, because notice it goes from the point F, which is actually just a point on the graph. So F is actually the point here. And one thing I haven't had good success with, because you probably can't see that very well, is the fact that that point is actually labeled F. Sometimes it just doesn't seem like those things show up in the right location or in the right color. I'm sure I could change that one to blue or something and it would look a little better. But then it aims in the direction of B, and notice again, B is the derivative. So the derivative, as we saw last time, produces actually the speed. And so in this application where the black is actually the path, that's the position, then the change of, because this is a classic what a derivative is, the change of position over time is a speed or a velocity. And notice you get the vector version of that. This is one of the biggest things I want you to take away, just because if you have more science classes later, the concept of what a vector really is. You understand the difference between what the green vector is telling you versus that 6.91 over there? Somebody want to try to articulate that? We talked about this last time. It's okay to screw it up, but what's the difference between the green vector and 6.91? How are they related?
6.91 is the magnitude of the green vector.
Correct. So that's actually, that might be 6.91 meters per second. That's how fast the Falcon is flying at that moment. And so of course, if I cruise to another location, why does that keep happening? If I cruise to some other location, notice the Falcon has picked up speed because now he's going 8.6 meters per second. What's the green vector? Isn't that what the green vector is? Is the 8.58? What's the green vector? What is
Shows
that?
the tangency of the line at that one spot.
Yeah, it's tangent. So it'll always be tangent to the curve, because at any second, at any moment in time, and if you take engineering with me, we'll see this is a big thing. At any moment in time, that's the direction the bird is flying. Now, 1 second later, because the bird got bored, it's going to fly off in some other direction, right? Because it's a fun path. The bird's Doesn't have to go to work each day. So he's like, let's have fun. So what is that green? It's tangent to the curve, but it's really telling you the direction that the bird is flying on top of it. So notice, as I said the other day, that in this case, the 8.58 is built into the vector. Notice the vector is right here, negative 3.94 in the X direction. And again, let's just stop and stare at that for a second. So notice I'm showing this so that you can see it. We're looking down from the Z-axis right now. Can you see the negative 3.94 in the X direction? So tough with 3D, but can you look at that and go, oh, look at that. He starts from here. And then it looks like it's about at 2. And so if I go 1, 2, 3, notice these are every other mark. So it's really 1, 2, 3.9, which is about there. Look at that. That's exactly how long the vector is in the X direction. What about Y? Y is 7 in the Y direction. So notice it's about here. I can't read those numbers, but they're every other one. So 1, 2, 3, 4, 5, 6. That doesn't look right. It looks like 7. That one doesn't look right. What am I doing wrong? 1, 2, 3, 4, 5. Looks like 6, not 7. What's going on there? Maybe I just don't have the scale very good. Now I'm all wonky and I don't have that home button. Where's my home button? I want to go home. And then we got Z, which I got to turn sideways to see. Notice the Z is positive 3, and sure enough, it looks like it's going up 3. And so when you describe something as a vector, you're making it so easy to do all of your math because you're never saying, you know, the angle. Like what you wouldn't want to do here is say this thing is flying, you know, southwest 20 degrees off of vertical and, you know, 52 degrees from 0. Like it's really hard to describe it that way, but if a vector is describing everything in X, Y, Z, and so you're getting not just the 8.58 because that's built into it. All you got to do is square all those numbers, add them together and square root them. And that's where you're going to get this 8.58, but you also get the direction it's flying on top of it. So that's why vectors are so powerful. So that's why, and it's an amazing way to describe something because it really gives you 2 numbers in one. It gives you the magnitude, 8.58, but it also gives you the direction, kind of all rolled into the same thing. Now, let's see. I want to show you something kind of cool because remember how we were talking last time? Like this is an application where this is literally the position of the bird at any given time. So we're assuming we're starting at time 0 and he jumped off the ground, if you will, over here at what looks like 003. Notice 300, the X is 3, and then sort of flew crazy from there. And so in this case, the derivative definitely is speed, but remember how last time we left the day we were kind of talking about without, what if this was just a normal equation that didn't have any purpose? Let's see. I think in the interest of time, I'm just going to say this rather than belabor the point a ton, but if this wasn't time and the R wasn't position, that wasn't the meaning of it. If it was just some random equation that had no meaning, kind of like when you say y equals 3x plus 2, what is that model? Nothing. It's just a line. It's just a line flying through space. Well, the same thing here, except it's just interesting. It's curving. What does the length of that vector represent? One of the things that's really fascinating about this, and I'll see if I can show this to you. What do you think is going to happen if I go in here and I double the time? In other words, I replace t with 2t. What do you think is going to happen to that curve? And actually, maybe I'll on purpose make up one randomly here really quick. Let me see, how do we do this? It was like, I'll make it easier to type in. Like I'll just say the sine. Let's do something different. T, how about 3t? And the sine of t and t squared. So this is just a random curve. And notice it's got a sine wave in it. Awesome, kind of fun. Cool. And so we made a vector on this the other day and we said, we thought the length of the vector was the slope of the curve, right? except it didn't seem like that was working. I want to just quickly resolve that conundrum for you a little bit, because I put some thought into that and realized there was something I was doing. It was kind of stupid. So what do you think is going to happen if I replace that t with 2t? So this is now just a curve in space. This is not something flying along. The derivative of this is not speed.
I think we messed with the t's on Thursday or something, and I think it just elongated the cosine wave.
Let's do it. So I just duplicated it. So if I double t, then does it make sense this first t turns into 6t? And if I double t here, then it turns into 2t. And if I double t here, since it'd be 2t squared, then it turns into 4t squared. Do everybody agree with that? Everybody happy? The question is, where's the new graph?
It's the same graph, it's just overlapping.
Is that true? Apparently it is. See how it's the same exact graph. Why would that be? That seems weird. Didn't you think it would like make it twice as long or something like that? But let's try to wrap our mind around why that would be. Well, think of t as just time. If it's time, what did you just do then by putting in 2t?
You gave if you were at any position on that graph, twice the time.
Yeah, it just kind of, it's not obvious that it actually doubled the time. It could have cut the time in half. In other words, if you wanted to take the sine of 4, well, in the new graph, you'd only have to put time 2 in to get the sine of 4. Does that make sense? So you actually cut the time in half. So it actually, all it's really doing is kind of just changing the speed at which the graph is drawn. So it's kind of interesting with this. This isn't modeling the flight of a falcon or something like that. But in a sense, if you were to graph it, it's kind of the speed at which this whole thing is drawn. So even in this situation, even though there's not kind of an application, the derivative of this still has to do with the speed at which the graph is drawn, even if it isn't a bird flying along it. So that's kind of interesting. So the derivative of this is still a velocity, even though it, is not defined as a position and so forth. That's what's really interesting. And then the other thing I want to show you is, what about the slope? Would you agree that, that was still an interesting question? If I think if I'm the bird or I'm an airplane and I'm flying this cool path, the concept that I'm, going up at a certain slope, does it make sense? It seems like I should be able to get that number. And again, we said, I was thinking the magnitude of that vector for our derivative, I was thinking the magnitude of that would be the slope, but it's not. It's actually the speed at which this graph is drawn. So if I was to do calculus on these two different graphs, I would get two different answers. That second one would have either a double length vector in the same exact location, or it'd be half as long. Notice how you have to think about that a little bit. I'm not really sure because the time would be half, so maybe it'd be shorter. So the vector lengths would be double. That's what you'd see that's different, because it would be showing you, oh yeah, those aren't the same graph. Well, they are at the same path, but they're not drawn at the same speed. And so those two vectors would be different lengths. And so you'd think, well, so your thought should be, well, I guess it isn't, the length of that vector is not the slope then, because I just got two different lengths for the same exact vector. So let me share a different screen, and you don't need to know this for your assignment, but I'm actually this seems like a really cool takeaway. So I'm just kind of wondering why that wouldn't be in a book. Because the whole fun of math is, and the beauty of it is to think and ask questions and, try to solve problems, try to apply it to something if you're application oriented. So what about the slope, side point, slope of a 3D path? And if you go on to Calc 4, I call this a path because it's kind of like a line in space. If it's a surface, that's where you're getting something that's, a 3D literal shape, like a cup, a paraboloid, or some of the a plane, is a 3D shape. It's not a path. But let's just think about this for a second. So if I've got, I'll just draw this from kind of the side view, but we'll still give it a name that's, I think I'm just going to use numbers for this, just to, no reason not to. So notice if I draw this in 2 dimensions, you sort of have no idea what that even looks like. But would you agree that whatever direction that thing is pointing, the slope is as it always was, which is rise over run? So, if I'm going to walk along that green vector, which represents the direction I'm traveling at that point in time, I just want to know the slope of that vector. But the question is, what are those 2 lengths? That's the thing that's fascinating about this. Can you think about what those would be?
Isn't it based on which component of the vector you're looking at? Like if you're looking at the slope of the z direction, that would be the x and y.
Yeah, that's kind of exactly right. So try to visualize this instead of just pointing, in the flat XY plane. Let's pretend it's pointing in the XY plane, except for it's also coming up toward us. Does that make sense? So, what would the slope of that be? Well, does it make sense that this distance here in the XY plane, does it make sense that actually is the run? So the distance it traveled in the XY plane would be the run. And the rise would actually be the distance in the Z plane. Can you visualize that? Maybe I'll go draw this in Desmos in a second. Actually, I probably should. Let's just do it right now. Delete. So I said 3, 4, 6. So vector V is going to be equal to 3, 4, 6. But then, so we're thinking about, what's the slope of that? And again, that's just, maybe this is the direction vector on a curving path, but we're just at one particular point right now. So let me draw the components of that vector that would be the slope. Does it make sense? I'll call this next one vector U. Because I'd like you to try to figure this out yourself instead of me just telling you, just because you can visualize this yourself. So I'll change colors on that just so that we can talk colors. I like that better. So we're trying to find the slope of the black vector. Notice that green vector is exactly below it. You can think of the green vector as like the shadow that the black vector is casting with the sun straight above it down in the XY plane. Does that make sense? So if we're talking about the slope of the black vector, do you see the rise and the run in this picture now? Do you see that the rise is the distance between the tips of those 2 vectors? And the run is that green vector that we just drew? So what I want you to do is see if you can write an expression for what the slope would look like. I'll draw a little bit more on this, bring it in for us and draw on it a little bit. I'd like you to think, what would the slope look like? What would the equation for the slope be? So if you agree that that distance is actually the rise, and this distance is actually the run,
I'm definitely glad you decided to model that in GeoGebra because it clicked once I saw it.
yeah, I can't imagine people
Mhm.
learning this stuff before.
Trying to imagine it in my head, I was like, I don't know why we wouldn't like lump the YZ planes together.
Mm-hmm. So is that visible? Okay. So I already wrote this down, but our run vector is actually, and I'll write it the way that GeoGebra is writing it because it's kind of cool too. Our run vector looks like that. What would our rise vector be?
Be 006, I think.
Correct. Because it's going straight up. So 0 in the X, 0 in the Y, and our Z coordinate was 6. So those are our two vector distances. And so I need those distances, right? Well, how do you get distance? Well, you know this. It's just magnitude. Magnitude, code for Pythagorean theorem. So the magnitude of the run vector, of course, would be the square root of 3 squared plus 4 squared, which we are lucky to actually get 25, which we can actually take the square root of. And notice the rise vector is just already 6. Like I could square them and add them together and square root them, but I'm going to get 6 again, aren't I? Maybe I'll put doubles so it doesn't look like an absolute value. So that slope is actually 5/6. So you actually have to split it. If you actually wanted to know the slope for some reason, you can't just take the magnitude of the 3, 4, 6 vector. Let's go do that really quick just to see what happens. If I take the magnitude of the V vector, 3 squared plus 4 squared plus 6 squared, and maybe you remember from Thursday, that's what we were doing, where you're saying we watch that vector get longer and shorter and so forth. If I do that, I get 25 plus 36, which is 61. If I take the square root of 61, I get approximately 7.8. So, what does that mean? The 7.8 is really the speed. It's not the slope. It's the speed at which the graph is drawn. If it, and again, it would be more normally the speed at which the bird is flying along the graph, that kind of a thing as a model. And by the way, that could just be visualized because in that previous graph where we said, hey, look, they're the same exact graph. If I limited the time on those two graphs to, time is from 0 to 2 seconds or something like that, one of them would be kind of twice as long. In other words, it's kind of like it got twice as much done in 2 seconds, if that makes sense. I'll go back and show you that before we get off that, since I still have it on my other screen. But the slope is a totally different number. Slope is rise of 6 over run of 5. So the slope is like 1. And of course, it's perhaps That's weird. Just lost that graph for some reason. I don't know what happened there, but I'm not going to redraw it. I was just going to turn it sideways so you could see the slope and go, yeah, that does kind of look like one. So in a sense, again, you don't need to know this, but as kind of a takeaway, ultimately the slope can be found by taking dz dt, or maybe I'll write it a little nicer. Z prime prime. Yeah, because notice this time I didn't do it with an equation. I just did it with numbers. But ultimately, if you take z prime of t and take the magnitude of that, and then you divide by x prime of t plus y prime of t. And I can't really write it the same. I kind of have to write the formula for them. Notice this is the magnitude of those two added together. I'm sort of doing the Pythagorean theorem on those two numbers. In a sense, that's what you have to do to find the slope. So anyway, that's just kind of interesting.
Doug, I'm a little confused because in Calc 1, didn't we learn that the slope at a certain point was the speed at which it's going at that certain point?
No, because the slope is really just the angle that it's at. It depends on what the letters mean. That's kind of the problem here. In other words, if I say r equals as a function of t, and on the other side there's a bunch of t's, it's a question of what do those letters mean. If I don't use t and I just use some letter like p or something, when I say t, you sort of think, oh, he means time. And I say that almost every problem just because that's a helpful way to think about this is time. But if r is actually the radius distance you are away from something and t is time, then the derivative is speed because you chose t to be time and r is a distance. So you have distance divided by time, that's a speed. But if t meant something else, if the parameter wasn't time, then its derivative isn't speed. So yeah, you're
kind of right now. The only reason we'd look at slope is like gradient at this point because we can find speed based on magnitude.
Mm-hmm.
So slope is literally just the gradient of the line.
Yeah.
All right.
How do you know what gradient is? That's a Calc 4 idea.
Well, I mean, I might not be using that word right. I just kind of mean that.
Oh, okay,
like,
I gotcha.
Yeah.
That's a Calc 4 word, a very charged Calc 4 word.
Oh, my bad.
Yeah, no, good for you. You're preempting the discussion. You're understanding why Calc 4 got invented. Because as soon as we start doing this on a surface where, again, I think of it as just hiking on a hill or something like that. Now all of a sudden the slope gets really complicated because I don't know which direction to point. You see how we have a path? We know exactly what direction to point. Our derivative tells us what direction we're traveling at any moment in time. Again, I like to think of it as like the headlights on your car. When you're traveling on a curved road, when you're turning on the curve, your headlights are pointing out into the trees, right? Because that's showing you the direction you're traveling at that moment. Now you got the wheel turning, and so a second later, your headlights are pointing another direction, hopefully, unless you go through the guardrail. But on a path, your direction of travel or your slope is easy to tell. But if you're hiking on a hill, what slope are you at? Well, it depends what direction you're walking. So it turns out in Calc 4, the gradient is a word that means the steepest slope. In other words, if you go, I want to get to the top and I don't care how steep I have to climb. I'm just send me up the steepest slope. That's like if you want to talk about slope, the only thing you can say is, well, do you want to know the steepest slope? I can answer that. But if you don't say that, then I got to say, well, what direction? What direction are you going? Oh, I'm going this way. Okay, well, then I can find the slope in that direction. Because slope gets more complicated when you're on a three-dimensional surface. Are you tracking with that logic?
Yeah, a little bit.
So that's what kind of makes Calc 4 really cool. So I don't want to overcomplicate this. It really is the case that most of this has to do with just speed. And so let's look at a really 14.3 talks about motion in space. That's the sort of the title. And this is limited to where, if I say r of t, r equals the radius distance to a point. And I'm not telling you anything we haven't been doing. This is, you already know this. That's the arrow that we've been drawing. That black arrow I just drew, that's exactly what that was. That's what a vector valued function is a point that's defined by a vector that starts at 0, 0 and just points at the point that we're talking about. So I graphed the point 3, 4, 6, boom. So that radius is a distance, and then t specifically is time. And since distance would be something like feet, and of course time would be something like seconds, then of course dr dt, which we also say is r prime of t, would be feet per second, and therefore speed, right? So that's the reason we study this, is to be able to actually to do calculus and say, hey, that's really cool that bee cruised along in this interesting path. And if you just know basic algebra, then you can actually graph its path. That's kind of neat. Maybe find an equation to model its path. But if you want to talk about other interesting questions, like how fast is it going or how far did it travel? That's the two things we're going to tackle now, is applications to calculus, both of which you've seen before, and the math of which is easy. Those are the two interesting questions that a calculus student can bring to the table. So 14.3 is how fast is it going at any point in time, and 14.4 is the length of the curve. So I'm gonna make up again, because I'm more interested going out the door that you just kind of learn how to think. I can make up a boring problem and kind of do it really quick, and maybe we'll do some of that too, but let's kind of look at a golf example. Let's see. So I'm going to try to draw this, and I want to see how much of this you can figure out yourselves. So I'll call this X and this Y, not Y prime. And this Z. How good are you getting at seeing those as 90-degree angles, by the way? I mean, those axes are at 90-degree angles. Are you able to see it that way?
Yeah, it's kind of visible now.
Yeah. So we're going to say that R of 0, what does R of 0 mean?
You're starting at the origin.
Your starting point. Notice that time is 0. At time 0, then where are you? Now, I am saying it is not at the origin. It's actually at this. Now, that might seem weird to you, but where are you then?
You're 80 feet in the air.
You're 80 feet in the air. Now, you might visualize that as somehow the golf ball is floating in the air, but no, this is just somebody teeing off on a tee that's 80 feet above the green. Does that make sense? So you're going to hit the ball and it's just going to fly down and land 80 feet below you. So you're kind of like hitting it off of a cliff or something. Super common. Every golf course has got a little bit of that. So that's your initial location. Now, what does this mean? So velocity, of course, is the derivative of position. So I just called it V of 0, but I could have also called it R prime. So what does that tell you?
Looks like you just hit the ball, maybe going really fast.
Yeah. Now, do you understand what that communicates to you? Do you actually know how fast he hit the ball? She hit the ball? It hit the ball? If you're given that information as a vector, is that cool? Would you rather I have told you, I'm making this up, But would you rather have told you that instead?
No, because we can find that.
That's a good answer. You can find that for yourself. What information do you get that you just lost if I tell you 300 feet per second?
Direction.
Direction. Like, do you see why this is cool? That's why vectors are cool. Because you have, and we've been talking about this, you have the magnitude right there if you want it. But more importantly, you have the direction the golf ball is actually hit. Notice they're all positive. And so if I was to try to attempt, I'm gonna try sort of a lame attempt at, what direction is this vector actually going? So I can't count 75 and 212, right? That's such a large number that I can't count 75 in the X and 212 in the Y. So I'm just gonna look at these kind of relative to each other and say, okay, well, I'll probably erase this part, but it's kind of like, okay, let's go that far in the X. I'm gonna call that 75. And then 212 is, well, like 3 of those. Would you agree with that? So it's like 3 of those in the Y direction. So something like that. And then finally 120, which is a little less than 2 of those in the Z direction. So maybe something like that. Notice kind of without those, maybe I will leave that in there. Without 75 there and 212 here and 120 there. It's kind of hard to tell what direction that green is pointing, because notice it's hard to see that it's going up. You can't tell that it's going up, but the Z was 120. So there's a significant vertical component to this shot. Does that make sense? Cool. And again, why is it called V0, not just V? Why didn't I just say velocity as a function of time? Why didn't I put a T here?
Because that's the speed at 0. It's gonna get gradually slower as it goes, or I mean, speed up maybe a little bit, but
That's exactly right. I mean, because of gravity, isn't its speed going to change? Speed is a scalar. You have to take the Pythagorean theorem to get the speed, but isn't that vector going to start changing immediately as soon as you hit the ball? Now, if there was no gravity, then it would just go that way forever and it wouldn't be a very fun game, right? God, lost another ball. But because there's a gravity vector pulling down on this thing, then it's actually going to be changing speed and direction constantly, right? But that's all you have. The cool thing about golf is or any thing like this. I throw a rock, whatever, shoot a gun, arrow, bow and arrow. The only thing I have control over is kind of the initial position and the initial speed, right? And after that, I just kind of go, I hope that lands where I want it to land, right? Now, let's further complicate this by giving it some wind. So I'm going to give it some wind. The wind is blowing. That's a pretty common problem in golf. That's why there's a flag on the stick. We need another color. Green.
there should be a Wii Sports Games, but calculus edition.
That's exactly right. Takes you 5 hours to actually make your swing because you got to do a whole bunch of calculus, but
But you always get hole in one if you're good at it.
you always get a whole one every time. So I'll give you a wind vector as well. Actually, I'm going to make it even more challenging. Let's say that the wind in the XY plane is actually 32 degrees. Instead of giving you it as a vector, which would be nice, I'm going to give it to you the way it usually is given. So I'm going to say the wind is at 32 degrees. And I would have to write a whole sentence to get you to understand what I just wrote, because notice it's 32 degrees from X toward Y. I could have just said 32 degrees because isn't that how you measure? Again, it's hard to maybe work in 3D, but don't you start from the X axis and work your way up? Isn't that positive? And so that would actually be positive 32 degrees. But I drew it in the picture, so that's simple. And we will say, I'm looking at my notes thinking, why did I write feet per second for that speed? That seems like it would be feet per second. I'm pretty sure it is feet per second, so I'm thinking I wrote it wrong. Let's say the wind is 20 feet per second. It has a velocity too. And I'll just kind of add that we'll say this wind is horizontal. Notice I'm actually making that a little nice. Does the wind have to be horizontal to the ground? Could it have a vertical component too? Sure. Okay, cool. And let's say that you also have, because I don't have to say this, you have gravity, because that's a major contributor, right? We got to consider gravity. This is actually pretty realistic. That's kind of the point of this question. Anybody know what's gravity? In this
9.8 meters per second.
Yes, 9.8 meters per second. However, we're in feet. What's the feet version of 9.8 meters per second? Anybody know that?
Is it 32 feet per second?
Exactly right. And it's down. So just to be careful, it's 32 feet per second per second. So I am going to change the wind to be an acceleration, just so that it makes the problem a little bit more interesting. But there's no reason I couldn't just make it 20. All that's going to do is okay. So this is what we know. So of course the question is, how's this going to fly? If I kind of go down here and draw some version of a green, here's the flag stick. And it's like, ooh, so we kind of want this thing to go fly through the air. And this is kind of what we're hoping is going to happen, right? So we can actually know exactly where this thing is going to go now as a result of this, because it creates a path. Now, the interesting thing about this question is, notice you don't know the path. In other words, you don't know the R of t equation. Do you agree with that? But in the game of golf, like the only thing you would have control over is the velocity. That's what's kind of so cool about calculus. I have control over the velocity based on how hard I swing, and that's all I know. So see if this makes sense to you. Could you write an equation now for the velocity, not the initial velocity, not v of 0, but rather v of t? So the question is, how does that 75, that 212, and that 120 change over time? Well, do you agree that the gravity's only effect is in z? So if it wasn't for the wind, then only the 120 would be changing. Do you know that? Now there's a wind resistance part that I'm ignoring, which is seriously significant. So we're starting with something simpler here. But thanks to the wind, we're actually going to get a boost in our shot. And again, I'm not giving you questions this hard in the assignment. I'm not giving you questions this hard on the test. I just think this is just so cool to learn, conceptualize. Just enjoy this. Don't worry about your grade. We're just learning. This is fun. So the question is this: I'll make this drawing a little easier for you to see. Does it make sense that this wind has an X component and a Y component? Do you see the right triangle that's on flat ground down there, thanks to the wind? Can you figure out how much of that, well, 20 feet per second of wind accelerating the ball? You should say, oh yeah, 20 is the hypotenuse. And if I take 20 times the cosine of 32, that would give me kind of the X. 20 cosine of 32 is 19.96. And this Y over here, since sine is the opposite of 32, then I'd say 20 times the sine of 32. That would be the Y. 20 times the sine of 32 is 10.598, so actually 10.6. This is, again, the strength of vectors, because you should look at this as totally confusing. If I'm up there hitting a golf ball, it's like, there's all these directions, I'm totally getting lost. But because we're breaking everything into X's, Y's, and Z's, this then would be our vector equation. Well, the X started out at 75, but what happened to it thanks to the wind? Well, it got a boost. Notice it's in the same direction, a boost of 19.96 times time. Now, just so that you kind of understand why I called this, why I gave that wind an acceleration, not just a velocity. If I didn't give it a acceleration, it would have been 75 plus 19.96. In other words, that's its actual velocity. You might have hit it at 75, but the wind was blowing at 20. I'm sorry, yeah, 20. 19.96, that's really close to 16.96. I can't even read my own calculator. It's like, that's almost 20. 16.96. So it actually gave it a boost of about 17, and so it would just be going faster. But with the wind accelerating it, then since the unit for this would be feet per second, if I multiply that by time in seconds, does it make sense? That time being in seconds turns that into a velocity. Cancel this X, cancel that X, now it's feet per second. That's why I have to multiply this by time, because I'm getting 16.96 feet per second faster every second now, since that was an acceleration. So it doesn't have to be an acceleration, it's just kind of fun if it is. And then didn't we also get a boost in the Y, since they're going the same direction? It was going to 12, but it's getting a boost of 10.6. What's happening to the 120? Notice the wind had no effect on the 120.
Gravity is pulling it down though.
Down. So down 32, and then again times time. So that's how those speeds are changing. Does that make sense? And as I said, I just made this simple by making the wind horizontal. I could have made the wind have a 3-dimensional component to it, and then that 32 would have had something else to go with it. Do you agree that's our velocity as a function of time equation now, which is kind of cool, because now it means we could know the velocity anytime we want, right? That's kind of fun. So if we knew how long this was going to be in the air, let's say it was in the air for 3 seconds, does it make sense we could plug t as 3 in and we'd know the velocity when it hit the ground as a vector? That's kind of fun. But I'm actually interested in this. Why am I interested in that?
Because that gives us the position function, I think.
Exactly. This gives us the path or the position function. The integral of velocity is position. The derivative of position is velocity. But again, this is the fundamental theorem of calculus in action because we can go back and forth from position to velocity to acceleration. So I'm really interested in that because then I'm actually going to be able to graph this in GeoGebra, so to speak, and I'm going to know exactly where it's flying through the air. That's what's so cool about calculus. Again, notice the only access you would actually have to this is the initial velocity. You can decide which direction to hit it and how hard you want to hit it. But you know, that's all the choices you got. Now you just stand there and watch it fly and hope you didn't, you know, suck at golf, right? And of course, real golf's harder because you can actually hit it with a slice and it spins out of control in different directions. And it's a terrible game. I don't know who invented it. Can you do that? That's easy. The integral of this is easy. What's the integral of that? You're just looking at these one at a time. What's the integral of that statement? You write it down ahead of me.
T
Yeah. 75 grows a T.
plus 16.96 t squared over 2.
Exactly. I'll just divide that on my calculator. 16.96 divided by 2 is 8.48. And similarly with everything else, right? The 212 grows a T, the 10.6 ends up divided by 2, which makes it 5.3. The 120 grows a T. So this is really cool because what can I do with this now? Like what interesting questions can I now answer about golf that I couldn't answer before? And by the way, we're not totally done because what happens when you take an integral?
You got
They're
constants.
constant.
Yeah. So do I care? Like, is that like, who cares? We don't need that. Do I care here? I'll have to say C1, C2, and C3, right? Because they're maybe told, do I not care? Is it like,
Those would be our initial position, so we would have to add the 80 in because that's on.
yeah. Notice if you put time t is 0 into that, you get this, don't you? So yeah, you need the constants. Otherwise, this isn't where you said it was. Does that make sense? So we said it actually started off, you know, we're above the ground where the flagstick is by 80 feet. So armed with that, we need R of 0 to be 0, 0, 80. And so can you fix it? Like, so those constants are not, they're necessary. Now, fortunately, this makes it easy, right? Because we put 0 in, we need 0. So do you see that? Okay, cool. Well, then that one's already right. I don't need that one because when I put time 0 in, I want location 0. So good, that one's 0. And the y coordinate is also 0, but this one can't be 0. It's got to be 80, otherwise I'm not going to get 80, right?
Is it not negative 80?
No, because this was positive 80. So when I put t is 0 in, I need 80 for z to come out.
Oh, okay.
So that equation actually is a little bit modified. Those initial constants matter. If I ignored that, then I'd be hitting from the ground and I'm going to get a totally different kind of flight path. So now I actually have the real equation for RFT, but what cool things can I do with this now? I mean, this is very exciting. Like what questions can I answer as a golfer?
Can model the path of the ball in the air.
Exactly. I got the path of the ball in the air. Now, what are the interesting places on that path that I might be curious about? What's the most interesting one?
Where it's going to land. Probably the highest point.
Exactly. Yeah, highest point is interesting. Where it's going to land. So let's answer the land. Where's it going to land? Because of course that's the whole game of golf. Because I didn't write this in here, but does it make sense you would know? I don't know if you've ever played golf before, but it tells you how far away that is. Like you know how far the green is away, how far of a shot that is. So, is it going to land? Is it going to land long? It's like, oh, I nailed it perfectly right toward the green, but then it landed way past it. No, it landed way short. It landed right on it, except for it was way over here. The wind blew it off course. So what do you have to answer to? This is just beautiful algebra, but it's like, okay, where does it land? How are you going to know where it lands? What do you know about it if it's landed?
The velocity should be 0.
That would be after it came to a stop. And to get the velocity to be 0, you'd have to come up with a force of the ground pushing against it. So right at the landing, it actually has a pretty big velocity, but then thanks to the force of the ground pushing against it, suddenly it has no velocity. So that's actually too complicated, what you just said. That's it.
Shouldn't it be on the ground? Like we should have a 0 vector?
It's on the ground. So what do we know about its position if it's on the ground?
You only know that its Z position will be 0.
That is exactly right. What's X and Y?
The goal.
Yeah, that's like the position, where this is located, but I don't know what that is. So, how am I supposed to know those? Well, the cool thing is you don't need to know them. Why do you not need to know them? Look at your Z up here. You should be saying, oh, cool.
Because once you solve for t, you can just plug that t into your x and y components.
Exactly. That thing only has one unknown, right? So if I need to set that equal to 0, there's only one unknown. I don't need to know the other ones. I can actually know the time. And if I know the time, then as Cheyenne said, I could plug the time into the X and the Y and I would know those too. So actually, I'm going to know exactly where this lands thanks to this logic. So of course you should say, sweet, all that studying, learning the stupid Pythagorean, the stupid quadratic formula, all that time I spent putting in my calculator, boom. Another beautiful application. I'm sticking -16 in for A, 120 in for B, 80 in for C, and I get 2 answers for this. Of course, we would reject this one. I'll just leave you to think about like, what is that though? Is that something that just doesn't make sense? But of course, the positive, we're lucky they're not 2 positive numbers, right? Because then we really have been confused. So we actually know the time is 8.12 seconds. And so I can go back then and say, what is R of 8.12? Throwing in 8.12 for every one of those equations. 75 times 8.12 plus 8.48 times 8.12 squared. I got, again, it's kind of a question of how do I write this, but I got 1,106. I'm just going to round them off. 1,168 approximately, because these are feet, so pretty close. And then 212, giving you time to process this, plus 5.3 3, 2,070, 71. Is this a realistic golf shot? Did I make up a good problem? Anybody know anything about golf?
I have no idea about that.
Average like length, I think, for like a hole in one, I think is like 300 to 600 feet.
Yeah, they're always measured in yards on a golf course. Like like a pro can drive a golf ball like 300 yards, so that'd be 900 feet. So
Oh yeah, you're right. You're right.
So it must be really windy, or you must be an incredible golfer. Like this is a little unreal. You hit it unrealistically fast, I'd say in this case.
World's farthest golf shot was 1,500 feet.
Is that true? Did you look that up?
Yeah.
So that's 500 yards. Yeah, and they actually have a contest every year, long drive contest, where the goal isn't golf, it's just who can hit that ball farthest. So that's probably where you got that from. Wow, 500 yards. That's amazing. So yeah, we're 15. This guy, whoever this is, like, wow, you smoked it. So, again, I'd say that's the most powerful. So isn't that isn't that amazing that you can actually figure out exactly where this thing's going to land now? And what did we know at the start? We knew 2 things. Where did you hit it from, and what speed and direction did you hit it at? And then thanks to calculus, we know exactly where it's going to land. So of course, we won't go down this road, but this would be a good project if the class was 3 weeks longer and so forth and we had time. But of course, the fun thing would be to actually do this realistic and not just kind of hit it this way and hope for the best. But what if I actually gave you the XY coordinates for the landing zone? Does this probably make sense to you? If I gave you the XY coordinate of this spot right here, and then you backed up and said, okay, well then what's my velocity vector need to be? In other words, what club do I need to choose? By the way, the club you choose gives you the height, because there's different pitches of clubs. Some kick them up in the air higher. And then how hard you swing is kind of the X and the Y. So the realistic question would be, I know X and Y, and then which speed should I hit this at? What speed and angle should I hit it at so it lands there? Isn't that weird that you could actually just figure that out, even with wind involved? Amazing.
So for that final vector that we got, is the magnitude the actual length that it traveled, or is it just the X and Y?
Yeah, now the length that it traveled, So if you were to draw that, because we're talking about, this is the location of that point. I'll just copy it up there. That's literally the coordinates of that point. Remember, we're thinking of this as kind of 2 ways. But that's the coordinates of that point. And what that would be measured, it is a vector. You can think of it as a vector. It's just measured from here. Does that make sense? Not from where we hit it from, because we said that was 80 feet higher, but this is our 0, 0. And so if you measured 1168 and 2070, boom, that's where it hit. So you're welcome to draw a vector there, but it's really just an ordered pair, isn't it? It's the same thing. It's an ordered pair with an arrow pointing at it. So the question is, how far did it fly? Well, how do you want to measure that? Do you want to measure it as a straight line distance to this? Or do you actually want to know the actual path the ball flew through the air? Does that make sense? For 2 reasons, I would say the length of the path, the length of the green dotted line is the correct thing to answer, because that's actually how far it flew. Why might you want to know this? Because remember, I said this wasn't realistic because of wind resistance, because the 75 is not going to stay 75. The wind's going to be slowing it down. So why would you actually want to know the actual distance it flew through the air? Well, from a physics perspective, does it make sense while it's flying through the air, the wind is, blowing on it the whole time? And so, if it blew on it the whole time, then I need to know how long it blew on it. Because we probably could come up with something about the wind resistance of what a golf ball experiences in wind resistance. And we probably could add that to our equation down here. That would be the thing that'd be really fun about this, is if I came back and said, okay, now not only is it 75 plus 16.96 T, it's also minus something for the wind resistance. So let's go see if we could actually find the length of the path. And really, this is a 14.4 question. And that's kind of why I ended up lumping these all together. The length of the path. And by the way, notice we know that that path now lives between, was it 8.12 seconds and 0 seconds? That's how long we're going to let this graph be drawn, if you will. So how do you find the length of something? Do you vaguely remember arc length from Calc 2? Now I say vaguely because remember that was like the last class you took. That was just last term. Isn't it amazing like how quickly stuff is gone from your brain at the time? You're like, oh yeah, I can do that. That's why I'm a big fan of reasoning and thinking and training your brain, because you've forgotten that now, right? And that wasn't even no time had passed at all here. In the real world, it's going to be a year or more before you actually need something like this. So, if I go look up how that worked, you may remember it's actually pretty simple. I'll rebuild the conceptual understanding of quickly, and then we'll be able to answer this question before we kind of leave class. But conceptual. When we were in 2 dimensions, this is what we said. We said, here, all these things flying along in some curve. And so we said, all right, you're here, and then you're here. And so we need to know the length of a curve. And so we said, well, if those 2 points are really close together, this distance right here could be conceptualized as a straight line, right? Now they have to be really close. I just drew them way too far apart for that. But if they're really close, that would work. And then we said, isn't this the change of X? And isn't this the change of Y? And so if I said, well, how long is that? Well, that's Pythagorean theorem. So isn't that little arc length up there nothing more than the square root of dx squared plus dy squared? All d means is a tiny little bit. It's not just any old y. X can't be 9. It has to be 0.1. It's got to be something tiny for this to work. Now, unfortunately, though, you're going to have to do it again and again and again, which is why you're going to need to add them all up, right? So in the end, we added these all up. And then we found it. So fortunately for us, what's the formula for this? It's not that hard. It's the integral of all of our values kind of under the Pythagorean theorem. In other words, you have one function for x, and again, what was our function? There it is. There's our function right there. 75t plus 8.48 t squared. That's one function, but notice the y function is a totally different one. So that's why I'm writing it this way. So I've got function of t. I've got some new function of t for our y component, and I've got yet even another function for z. Then what am I doing with those? I'm just doing Pythagorean theorem on them. Square it, square it, square it, add it, take the square root of it. And notice these are functions of t. So maybe I'll add to this. These are, t's. It's like these are times. In our case, they're times. Remember a second ago, it's not like a path has to be something, time. The t doesn't have to be time. Okay, cool. So what is that for us then? So for our example, my time went from 0 to 8.12. And I just have to take, well, the integral of all that stuff. I don't know if you remember this, you probably don't, but given the fact that we're taking an integral of something that is square rooted and squared, being able to manually take that integral yourself, like a second ago, we took the integral of 212 and we said it's 212t. Oh, that was easy. But you're not going to be able to take the integral of these things very often. I actually left one part out of it. What were these? Can you tell me what I left out of this? What's different? What's different between these two things? What is this dx here? I didn't say x.
To make it prime, make it derivative.
Yeah, these are derivatives. And so these are primes. These are derivatives. Because that's a tiny length. Very important oversight. Okay, so those are actually derivatives. In other words, I guess if you wanted to write it this way, you could just call that v of t, like these are velocities, right? Well, in our case, didn't we already have that? Like we started with a velocity. Isn't that our velocities right there? So that's all I'm going to be doing. I'm just going to take those three expressions, boom, 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 square them, add them together and square root them. $75 plus 16.96. See if I can squeeze all of this into one thing. I'm going to take that and square it and then add that to 212. I think it was 5.8. Was it 5.8 or 10.6? 5.3. So if we were given from the start a position function, then we would have had to take the derivative, but in our case, we already had it. And then, of course, I'm going to have to take the square root of all of that with respect to t. Can you appreciate this isn't happening? Now you could multiply all those out because can you see you're just going to get a parabola into there? In other words, 16.96 t squared, you're going to get just a giant parabola. But you may remember, and I doubt you do, I don't know why you would, but you may remember that if you were taking the square root of, say, t, I'll just make it x squared plus 3x minus 2 or something like that. That's not an easy integral to take. This is where we're making all these completing the squares and trig substitutions, trying to come up with some way that I can take the integral by hand. Very difficult to do. So it's not that you couldn't make some progress with that, clean up what's in there in green, but these are often not possible by hand. I should say usually. Somebody would have to make up a canned book problem for this to work out. But the cool thing is, can't we cheat? Can't we go into Desmos and just type that Zambridis in there and get an answer?
Yeah, we can.
Yeah, baby. I'm looking at my notes to see if I already did this. Looks like I didn't, so I'm going to do it really fast. In the interest of time, I'm just going to stick it into my handheld calculator. because I think that'll be a little bit faster. So I'm going to say the square root of 75 plus 6. And I got to say X, since I'm doing this in my graphing calculator, I got to say X instead of T because I don't have a T. 212 plus 5.3x, close the parentheses, square it, plus 120 minus 32x, close the parentheses, square it. And that's going to give me some just crazy graph. I know I have to go from 0 to 8.12. So I don't really care what the graph looks like, but I'm going to that integral button behind calc. So it's going to take it forever to graph this because it's such a crazy graph. So if I say second calc, take the integral of that for me. It says lower limit, I say 0. It says upper limit, I say 8.12. And I want to know if you think this is realistic. Using the TI-84, I get the arc length or the path length. See if I got this right. 2,319. Is that realistic? Does it feel realistic? A little long or a little short to you? To me, it feels short. Why do I think it feels short? And I did actually make a mistake and I caught it. I caught it because I stopped to think about this. Why does that seem short to you? Or I should say me. Remember, it's flying through the air, right?
Oh yeah, because just the Pythagorean theorem on 1168 and 2070 should be pretty long, and then that's going to be a lot longer than that. So
Exactly. Like if I do the Pythagorean theorem just on this horizontal distance right here, I think I'm going to be over 2,300 for that alone. So it just feels like the curve is going to be way longer, right? That just doesn't seem right. Well, my mistake was looking back up here, I stuck that 5.3 in right there for my coefficient instead of 10.6. So it should have been 212 plus 10.6. And I typed 212 plus 5.3. So I got lucky in the sense that and I don't think I screwed the rest of it up. 120 minus second quit graph. And notice I screwed it up here. So I'll leave it in red to embarrass myself. Second calculate 0 to 8.12. This time I got 2,461. That still feels a little short, but at least I'm happy it was a little bit longer. Now, with respect to the picture, if I just did Pythagorean theorem on 1168 plus 2070, I get 2377. That's if it went straight from here to here, right? So it's certainly longer than that. So it kind of took off from here. So at least I know it's more than that. That's 2377. That still feels, it's only 100 feet further. It still feels a little on the short side, but it's not, it's working. So you've seen a couple of formulas here. All I want to do really tomorrow is just like this was kind of fun because I gave you a realistic question. We sort of asked what I would consider to be the two most interesting questions of this. How far did it fly? And, you know, where did it land? We were able to answer those things to calculus. But involved, you know, integrals in both cases. But I just want to make up some random problems that don't necessarily have an application and practice this a little bit. I'd like to do it right now, but we're out of time. So that's what we'll do tomorrow. And then we'll kind of see where we land after that.
Sweet.
Good to hang out with y'all,
Thanks, Doug. See you tomorrow.
Thanks, Doug.
friends.
Yeah, thanks.
I had a question about a problem on 14.2 homework.
Sure. Right now. Cool. Which one?
It was number 4. And my problem was that for the first version they gave me, so I started out by doing the dot product to find the angle, but I ended up with cosine of theta equals -3 over square root of 5. And I think I ran into a domain problem when I tried doing that. So I was just wondering how I should have tackled that.
So you probably had a different problem than this.
Yeah, I wrote down the problem that gave me that result.